Good afternoon. Welcome to session 13, which is about design guides. This is an opportunity for the working group chairman to report back on some of the key issues that are affecting tall buildings in today's environment. We have 5 presentations, 20 minutes each, and then 25 minutes at the end for some discussion. First up is Sun Choi. Sun Choi is going to report back on the Outrigger System Design Guide that she is leading for the Outrigger Working Group. Sun Choi is the Senior Principal with Thornton Tomasetti. Over to you, Sun.
Hi, I'm Sun Choi from Thornton Tomasetti. I believe it was late summer last year that I had a pleasure having lunch with Professor Sang-Dae Kim. While he was sharing his visions for concept of tall building, he said he would like to establish several working groups to develop design guidelines. And he asked me if I can lead one working group. After such a nice lunch trip, I didn't have a choice, but I have to say yes to his request. But at least he was very nice. He gave me 2 options to choose from. And I chose Outrigger Working Group over Column Shortening Working Group, which Ahmad Abdelajak is leading right now. It's because I figured that if I chose Column Shortening Working Group, it would require a great deal of lab testing, research, and construction survey data, of which I was not capable of. And also, I was not the most qualified person to undertake that group. When I returned to my office in the state, I shared this news with my colleagues, Mr. Len Joseph, Mr. Bob Sin, Ms. Corey Quicken. And I was lucky because they agreed to work with me to write a design guide together. That's how the Outrigger Working Group was started. During today's presentation, I'm going to highlight how the Outrigger Working Group is organized and talk about the working group's initiatives. And also, I'm going to talk about Outrigger Design Guide goals and topics, as well as the publication plan. The Outrigger Working Group is comprised of 4 co-chairs from 3 structural engineering companies with numerous tall building design with Outrigger systems. The 4 co-chairs are Mr. Len Joseph and myself from Thornton Tomasetti, Mr. Neville Matthias from SOM, Dr. Goman Ho from Arab China. In addition to these 4 co-chairs, we have 19 members in the working group who participated in Design Guide draft peer review last spring. They have been selected by Council of Tall Building to review and comment on the Design Guide draft. The members are Mr. Ahmad Abdelajak from Samsung, Mr. Chuck Bizek from SOM, Dr. Ryan Chung from Dongyang, Mr. Ramin Gilsengs from GMS, Mr. Andrew Hawkins from WSP, Mr. Yashiyoshi Hitomi from Nikon Seiki, Mr. Ronald Johnson from SOM, Professor Sang-Dae Kim from Korea University, Mr. Ron Clemency from MKA, and Corey Quicken from Thornton Tomasetti, Mr. Peng Liu from Arab, Mr. Lady Novak from PCA, Mr. David Scott from Arab, Mr. Bob Sim from Thornton Tomasetti, Professor Fei Fei Sam from Dongji University, Mr. Paul Sang from Arab, David Vesey from Arab, Mr. Masayuki Yamanaka from Obayashi Corporation in Japan. If anyone in today's audience is interested in participating in Outrigger Working Group's activities, please let us know. We anticipated that our very first design guide will require modification in the near future to incorporate new subjects and to incorporate advanced technologies and methodologies that become available. The first and second and further edition will follow continuously. Our working group's primary goal is come up with comprehensive design guidelines for Outrigger system. The design guideline will provide many design examples of the project that can be used as a reference. There are many unresolved Outrigger design and Outrigger construction-related issues. Although we are not capable of providing clear directions for all matters at this point, we are trying to initiate discussions among colleagues and encourage them to raise their opinions and share their knowledge about this subject. Through this exercise, we expect that we can arrive at a consensus on many of these issues that create a need of design guideline in the first place. The design guideline will consist of introduction of Outrigger system, design considerations and recommendations, project examples representing different types of core and Outrigger systems, special topics related to Outriggers and references will be also provided. The core and Outrigger system is often selected as a lateral load resisting system for tall or slender buildings where overturning is large compared to shear, or where overall building flexural deformation is a major contributor to lateral deflections. Outrigger transfer overturning moment in core to the exterior columns. Using Outrigger system, Outrigger system reduced overturning moment in the core and also relax the foundation load concentration underneath the core, especially for tensions. The Outrigger system can be very efficient and cost-effective solutions to satisfy submersibility requirement required for the tall and slender buildings. Since core and Outrigger system is indeterminate, distribution of forces between the core and Outriggers depends on the relative stiffness of each element. For maximum strength, efficiency, and serviceabilities, the Outrigger can engage individual mega columns that carries large portion of building weight, or engage multiple perimeter columns through the belt trusses. There are many different core and Outrigger systems depending on the material selections, geometry, architectural layout, and stiffness requirements. They can be constructed with steel, concrete, composite, or mixed construction as well. Although there are many advantages of our Outrigger system, there exist several disadvantages of the system that needs to be addressed from the beginning of the project. Coordination of Outrigger location is very important as it requires large space to work with, from floor planning with a core and column alignment to the vertical floor arrangement to locate Outrigger levels. If Outrigger engages with concrete columns, long-term differential column shortening between the core and concrete column become a concern as well. So as needed, construction sequence has to be modified, and also the potential vertical load transfer between the core and the column has to be addressed. The design consideration and recommendations, including appropriate conditions of the Outriggers and optimal Outrigger locations. By the way, the design consideration and recommendation in our report is not listed with bullet points or step-by-step numberings. It is because that depending on the Outrigger systems, materials, locations, and relative stiffness of Outrigger systems, the requirement for Outrigger system would be different for each project. Therefore, we focus on more general discussion of Outrigger system so that they can be applied to the projects with various conditions. Load paths. Understanding load paths is very important. Depending on the system, the load paths could be through the concrete outwalls, single diagonal members in Outrigger system, or it could be floor diaphragms at the top and bottom chord of Outrigger walls or belt wall trusses. And also, once load path is well defined, the collective force with overstrength factor for seismic load shall be considered following appropriate load paths. As mentioned earlier, differential column shortening effect is very important and it has to be considered. Construction sequence analysis shall be conducted to establish the accurate the column shortening effect. To reduce the column shortening effect, outrigger construction can be delayed joint can be provided, or collector shim plate or oil jack construction joint can be provided during the constructions. I believe this topic will be further developed and discussed by column shortening working group. Next. The material selection depending on multiple factors, including the required design strengths, required stiffness, space limitations, connection forces, details, material availabilities, construction method, schedule, and economies. Based on these parameters, material can be selected to suit the best interest of the project. In case where outrigger links expose column with a temperature control inner cores, the large forces can be generated induced by the temperature differential. Although it is not currently required by any code, we recommend that designer must consider temperature in the load combination with wind and seismic, because differential temperature can be present with wind and seismic event. Reduction is justifiable, but how much of the reduction in temperature shall be discussed outside of our Outrigger Working Group. Although Outrigger system is very common in building constructions, the Outrigger system is not listed as a seismic load resisting system in any code. So the response modification I value is not defined per code. The Outrigger I value should be somewhere between the core alone and dual system, depending on the relative stiffness. Therefore, structural engineers are using low I value associated with a core alone system for the Outrigger system and deal with higher seismic forces that the system may not experience. For special moment frame, structural flexural bending capacity of the column has to be at least 1.2 times of that of girders. If outrigger wall is spanning between core and the perimeter columns, the outrigger wall could be considered as a deep beam. If that is the case, how do we satisfy the strong column and weak beam requirement in this case? While we are doing research, we find that some structural engineers only using concrete or steel truss outriggers if special moment frame is required, because horizontal chord of the outrigger truss has very small flexural capacity as compared to 1 or 2-story tall concrete wall. However, shouldn't the entire outrigger truss shall be considered as a deep beam? If that is the case, we're not sure if this is acceptable. We also noticed that one engineer trying to provide a slat, 25-inch slat between the concrete wall and perimeter columns to satisfy the strong column and weak beam approach. Should such a shortcut be acceptable? There is no answer for this one at this point. The another ongoing debate is the application of overstrength factors. In case outriggers or belt truss is transferring interior or perimeter columns to mega columns, overstrength factor shall be applied for the outrigger system in this case. However, do we have to use this overstrength factor for all outriggers and belt trusses? Unfortunately, there appears to be no definite answer to these questions either. To design structures more accurately with the understanding of actual behavior of the building during the extreme conditions, we recommend that performance-based design shall be conducted. In case of a life safety performance level, The major structure members shall be kept in the elastic range during the seismic event, high seismic event, I mean extreme seismic event, so that building can sustain the damage. In that case, we don't need I values. Strong column weak beam requirement is not necessary anymore. Overstrength factor, we don't need to satisfy any of these issues. Therefore, performance-based design is highly recommended for the tall buildings or buildings in high seismic zone where the Outrigger system is very complicated, or Outrigger system contribute to the overall building stability significantly. Until 1970s, steel has been used widely for tall building applications. Especially tubular steel system has been widely used for super tall building design. Since 1980s, concrete has been introduced to high-rise applications, and Outrigger has been developed and widely used. We'll give you Outrigger examples that can be related to your project in the futures. One of the first Outrigger example is First Wisconsin Center. It is an all-steel system. The 42-story steel tower has 2-story tall steel Outrigger trusses linked with steel belt trusses at 2 locations. Engineer reported that a 30% increase in overall lateral stiffness was achieved through these Outrigger systems. Second example is Jinta Tower in Tianjin, China. This was completed this year. This 74-story tower has 8:1 aspect ratio. The lateral load resisting system consists of flow moment frame, the buckling restrained slender steel plate shear walls, linked together with the steel outriggers and belt trusses. Pushover, parametric, and sensitivity studies were conducted along with a performance-based design. Trump Tower is an all-concrete system example. This tower is the tallest concrete tower in North America. This 92-story tower has an aspect ratio of 8:1, and it has 1.7 meter thick by 5.3 meter deep concrete outrigger wall. This concrete outrigger wall was introduced to transfer columns at the setback levels. Strut and tie modeling was employed for this outrigger system. From spatial analysis of the time-dependent shortening effect, additional forces determined by construction sequence analysis were incorporated to the outrigger wall design. As a result, construction-related postponement was special connections to directly mitigate the issue of gravity load transfer through the outrigger wall was eliminated. Mixed steel and concrete system example presented here is One Rincon Hill in San Francisco. Both tower has 2 lines of outriggers engaged with the 4 large columns. The 4-story tall steel K-bracing outriggers were introduced.
2 minutes.
Okay. The brace themselves is buckling restraint braces. Next example, Shanghai Center, also an example of mixed steel and concrete system. The lateral system of this system has 9-cell concrete core, 9 mega columns linked with steel outriggers that is also linked with steel radial trusses. The performance-based design is conducted for this project as well. Another example is virtual outrigger example employed for Tower Palace Seoul project. 300 millimeter thick floor slab was introduced to create a diaphragm action that was engaged with 800 millimeter thick belt trusses. The advantage of these indirect outriggers includes less restriction on the floor layout, no significant delay for the construction, elimination of vertical load transfers, and elimination of differential column shortening effect. One of the special topics related to outrigger system is mechanical damping incorporated in outrigger systems. The image is shown here is the St. Francis Shangri-La Place project in the Philippines. The pairs of viscous damper connecting outriggers to column reduce the building acceleration by 35%. And also, next one is the buckling restraint braces. I'll quickly wrap up my presentation with a publication plan. Right now, the first draft was developed. We collected the comments from 18 colleagues that is around. The final file will be sent to Council of Tall Building end of this year so that they can publish next year. Thank you very much for your attention and interest in Outrigger Working Group. We look forward